Why haven't torched in the first place?
All right, how's it going?
That's good.
I'm impressed people are here because it's gorgeous outside.
I think that's a testament to us being the real computer science major.
Yes. Bonus points, right?
We're all vampires.
Yeah.
The first one?
All right, so how are things going? Week 10, last week of the course. So, but there's more to come in spring, so the fun won't end. Questions up to here? Yes.
I was wondering for the max value function.
Mm-hmm.
I'm confused at where you store, like, so the max value is going to show you the max value for your bag or whatever.
Mm-hmm.
But where do you store how many of what item?
So that's a really tricky part, okay? And in the past, I've actually done that as a bonus option if people wanted extra points, but I decided to make it part of the assignment for this class. But you can view it as a, once you've got everything else working, try to get that working too, right? It's probably worth 10 points if you don't do any of it. Basically, your max val function, you want it to return two things. So you want to put in a capacity, and you want to get out maximum value, but you also want to get out a list of items, right? Which items and how many of each item you need to get that maximum value. So your first question is, how am I going to store that? And my suggestion has been just make an array, right? Index your items, make an array. Element 0 is how many of item 0 you want, element 1 is how many of item 1 you want, element 2 is how many of item 2, and so on. But you can store it any way you want. You could make a linked list of items, you could make a linked list of how many of each item you want, you could make a really ridiculously big array and just store, you know, item 1, item 3, item 1, item 3, item 2, or whatever, but come up with some way to store that. And then you want max val to return these two things, a list of items and the maximum value that you get using that list of items. So think structure, right? Make a structure that holds both of those things and return one of those items or a pointer to it, if you like. And then inside the max val routine, we have a loop, right? So for I equals 0 to whatever n is. So the possible value we get if we start with item I is the value of item I plus max val of capacity minus the weight of item I. And you're iterating over a loop, and remember, highest value of possible. So best equals 0. If possible is bigger than best, best equals possible, right? The usual way to detect a maximum. But you need to do one more thing. Max val is not just giving you a maximum value, it's also giving you an inventory that leads to that maximum value. So you want to remember not just the maximum value, but the inventory that gave you that. So you want a local variable best and another variable like best inventory, right, which corresponds to best. So that when you come out of this loop, then best equals highest possible value, and best inventory is the inventory that got you there. So how do you make that best inventory? Well, when we consider item I, we take the max value of our diminished capacity, we add it to the value of item I, that's our new possible value. If that's the best value we've seen so far, we want to remember that value, but we also want to remember the inventory that this gave us. And we want to update it by adding one more of item I. So either add an item I to the end of your list or update the index that's counting how many of item I you want or something. So that when you come to the end, you have not just the maximum value, but you also have the inventory that gives you that value. And like I say, if you do all this earlier enough, you can finish this max val loop, debug it, get it working, and then kind of go back in and completely rewrite it using the exact same structure, but have max val return these two pieces of information, keep track of both pieces of information here. And then at the end, you've got your best inventory and your best value, return those as the return value for that outer call to max val. And then when you add caching, you need to cache both of those also. Because if you call max val for capacity 15, you've already calculated that. You're not going to do all the recursion, you're just going to read the value out of your save array, your cache. So you need to have cached up not just the max value of 15, but the inventory that gets you to 15. So it's almost like completely redoing the max val function to have this extra piece of information. But max val itself is really a few lines of code. Right? It's just getting the right few lines of code that makes it so tricky. But then changing it to add this thing in is not, rewriting 200 lines of code. It's really a for loop. Does that help?
Yeah.
Okay. So other questions or comments? We're going to do all of sorting today and Wednesday. And I want to leave a bit of Wednesday if you have questions. I might do some kind of like review on Canvas or something, but study everything. It's a review. Yeah?
I think a real good question. One of the quizzes, in quiz 6, talk about like heaps and that kind of stuff.
Yeah, everyone's been asking me about heaps today, and I finally figured out why, because it's on the quizzes, so we'll do heaps today. All right, well, we did bubble sort, we did selection and insertion sort, correct?
Yes.
Okay, so I think we're up to, did we start merge sort? Okay, so let's do merge sort. All right, so I've got 13 cards and they're kind of all scrambled up together, and I want to sort them. Well, here's what I'm going to do. I'm going to use recursion. I'm going to say, can you sort those 6 cards for me, or 7 cards, and can you sort those 6 cards for me? And I don't care how you do it, because I'm just the main program. But no peeking. No.
Oh, sorry.
No, I'm kidding.
I fold.
All right. Thank you. Hey, they both did them from smallest to largest. That's good. All right. So I have my original set of 13 items to sort. I split it in half, and I called functions to sort each of those halves. Okay. I haven't done any work myself yet. Okay, now I need to turn these 2 piles into a sorted pile. Here's what I'm going to do, and I need to do it like this. So I'm going to start with the smallest from either of these 2 piles, and that's going to be the first thing I put in my output, so that's my ace. Oh, the ace got on top. Okay, hold on.
But it sits on top.
It was an underspecified subroutine call.
Well, to be fair,
So you
it
should
just
check
says
the
sort of
document.
nitty.
I know.
Yeah, but there's only one logical way to do it.
I thought of it afterwards, but then I figured I'll just take a chance. Okay, so there's the 2 sorted piles. Okay, simply compare those 2 numbers on top and pick the smallest one. That's the ace. That's the first thing in the output. Now compare the 2 numbers on top, pick the smallest one. Compare the 2 numbers on top, pick the smallest. Compare the 2 numbers, pick the smallest. Is this hard? No. You're comparing 2 numbers and you're picking the smallest. There's the 8. there's the 9, there's the 10, there's an 11, there's a 12, and now there's nothing left in this pile, so I'm just going to take this one. And guess what? My cards are all sorted. It's like a magic trick. A really bad one.
No one will be impressed.
All right, so how do we merge sort? Sort first half of data, sort the second half of data, and then merge those sorted halves. That's the whole algorithm. The trick, of course, is that how do you sort that first and second half? Use a merge sort. Oh, yeah. Thanks. All right, so merge sort. Sort the first half of the data, sort the second half of the data, and then combine those two sorted halves into your output. To sort the first and second half, we call merge sort. Okay, so it's recursive. And then to merge those two sorted halves is this operation we just saw. Simply look at the two sets of sorted information, take the smallest from the top of one array or the other, or maybe the end of the arrays, put that in your output, and then take the smallest of what's on top and keep going. And if one of the piles gets completely exhausted, then you know all the other numbers are going to come from that other pile, so you can just take that and just add it onto your output.
So if you keep cutting in half, aren't you just going to have it like 1, 2, 3, 4, 5, 6, 7, like they would all be in their own piles?
So if you keep cutting in half, eventually you get down to a pile with only one item in it. And to sort that, you don't have to do anything, just return that one item. It's already sorted. So we need a base case. If only one item, then just return. Otherwise, if you have two or more items, split your array roughly in half. Doesn't have to be exact. If it's an odd number, that's okay. Split it roughly in half, sort each half, and then interleave them. So here's merge sort of n items. So if n is less than or equal to 1, we just return. Otherwise, sub 1 is maybe the data elements from 0 to n over 2, and sub 2 is data from n over 2 plus 1 to n. Don't worry about the index origin, n plus 1 stuff. Right? Make two arrays that represent the two halves of the data. Merge sort sub 1 and merge sort sub 2. And you got to tell it how many elements you have, but that's just n over 2 plus or minus 1. You got to deal with odd numbers and all kinds of new annoyances. But basically call merge sort on those two. And then we want to interleave these two arrays. So so while sub 1 and sub 2 have data left, and this is heavy pseudocode now, if whatever the last element in sub 1 is bigger than whatever the last element in sub 2 is, then sub 1 last goes into your output array and remove the last element from sub 1. Else do the same thing for sub 2. So it's this interleaving process, right? And writing code to do this is really annoying. Okay, it's lots of edge cases and lots of wondering if you have n items in your array and you divide your array in half, what's the index of the last item in the first array? Is it n over 2 or n over 2 minus 1 or integer n over 2 plus 1 or what? And it's annoying, but it's something you work through. But the algorithm is very straightforward, right? Take your array of data, chop it in half, merge sort this half, merge sort this half. Now, start at the beginning of each array, right? And take whichever value is, let's say, smaller, to do what we did with the cards, move that into your output array and move your index for that array up 1. Right? Now take the two elements that your indices are pointing to, take the smaller, put that in your output array, move that index. And keep going until your indexes are past the end of each subarray, and then you're done. Does that make sense? So it's a classic divide and conquer algorithm. All right, how do we sort this? Cut it in half, sort each half, put the solutions together. It's almost definition of divide and conquer. And other than the annoyances of working with arrays in C, it's really easy to code. But arrays in C are just like goofy to think about in this way because they're memory addresses rather than actual indexes. But if you had a linked list, this would make a lot more sense. Because linked lists, we have a nice way to start at the beginning and move forward one at a time and so on. So there's lots of variations on how you actually implement this. For example, we don't usually take our data and copy it into other arrays because that takes a lot of operations. Right? This right here is order n. And that's kind of unfortunate. But we can work with an array of data in memory. We can pretend that it's only half as big an array by simply saying our data starts here, but it only contains this many things, right? And we can work with the second half of an array by saying, well, our array begins at this middle point and contains this many things. So implementation details. So this merging step, this interleaving, is basically order n. Right? You have to go through a total of n pieces of data as you put them into the output array one at a time. But each time that we split our data in half, we have to go through this whole merge sort algorithm, which is roughly order n. So the question is, how many times will we recursively call merge sort? And if we're splitting n items in half each time, that's going to be log n, roughly speaking. So this is roughly order log n times. So an entire merge sort is roughly n log n, which is nice. It's a whole lot nicer than selection, insertion, or bubble, which is n squared. Now you could make this inefficient. Instead of splitting our array in half, we could split it into two really lopsided piles, one containing one number and the other containing all the other numbers. And this will still work, right? The problem is that we're going to call this roughly n times instead of log n times. And in the end, we're going to split our thing into individual piles and then start interleaving one card with one card and so on.
Doesn't it almost become a bubble sort at that point?
It becomes a something sort, I'm not sure what. So I could split into, I've never tried this. So let's split into two piles. There's a 7 and a queen. We're going to merge sort this. Well, that's already sorted. So we'll move that over there. And then we need to merge sort this pile. So we'll split into two piles. This is already sorted. And we'll merge sort this. I'm just going to do 5 cards. That's already sorted. That's already sorted. We merge sort this and we're done. And then we're going to interleave these two piles. So that's going to go like that. And then we're going to interleave this. And then we're going to interleave this. and then we're going to interleave this. So it looks like an insertion sort. But I'm guessing there's some variation on that that'll make it look like a selection sort, maybe. Maybe not. Alright, so that's merge sort and log n. Pretty nice. Let's look at, did we do radix sort?
Nope.
Let's look at radix sort. Alright, let's do a radix sort on these 7 numbers. So here's the algorithm. We start off with the least significant digit. And we sort these numbers based on this rightmost digit. So just looking at single number. And as we sort these, if we have 2 numbers that have the same last digit, we have to preserve their order. We don't want to swap them. So here's one way to do this. Make 10 passes through your data. First pass, we're looking for anything that ends with a 0. And we don't find anything. Second pass, we look for things that end with a 1, and we find 1, 3, 7, 6, 1. Then we look for 2s and 3s and 4s and 5s and 6s. There's a 4, 7, 2, 3, 6. And 7s, there's a 4, 2, 1, 3, 7. And 8s, there's a 2, 8, 8, 8, 8. And a 3, 2, 7, 6, 8. And 9s, there's a 1, 4, 3, 7, 9. And a 2, 8, 8, 8, 9. And now we do exactly the same thing, but on the second digit. So we look for 0s, 1s, 2s, 3s will be 4, 7, 2, 3, 6, 4, 2, 1, 3, 7, 4s, 5s, 6s, 1, 3, 7, 6, 1, 7s, 1, 4, 3, 7, 9. Did I miss a 6? I did. 3, 2, 7, 6, 8. Thank you. 7 right here, and then an 8. 2, 8, 8, 8, 8.
Why did you put the 6 there?
Okay. Seg fault. All right. 1, 3, 7, 6, 1. 3, 2, 7, 6, 8. That's all the 6s. No, we had 3s.
Second fault.
No, we can go backwards. All right, there's the 3s, there's the 6s, there's a 7, 1, 4, 3, 7, 9, and 8s, 2, 8, 8, 8, 8, and 2, 8, 8, 8, 9.
So if there's duplicates, it just grabs the first one that comes first?
You have to do them in the same order, yeah. So if there's duplicates, first one will go first, second one will go second, and so on. And that's really important.
So you start with the ones place because, you know, all the numbers could be different lengths or what?
You start with the 1s because they're least significant. They have the least to do with the final sort order. Intuitively, it usually feels like we should be doing this the other direction. We should start with the most significant. But then you have things almost sorted, but you have something that ends with a 1 and it comes before something that ends with a 2, which doesn't really make sense. That doesn't really determine the ordering. It's really this most significant digit that's going to affect the ordering.
So isn't this worse than n squared?
Well, let's see. Let me finish this up because we started it. So there's a 2, there's a 3, 4, 5, 6, 7, 1, 3, 7, 6, 1, 3, 2, 7, 6, 8, 2, 8, 8, 8, 8, and 2, 8, 8, 8, 9. We'll get there. Alright, so 4, 2, 1, 3, 7, 3, 2, 7, 6, 8, 1, 3, 7, 6, 1, 1, 4, 3, 7, 9. And then last case is most significant digit. And basically what we've got is we've got these things sorted as if they were 4-digit numbers. Right? And now we have a 5th digit, so we arrange them based on that. And if they were the same 4-digit number, they'll be ordered accordingly based on the 5th digit. So 1, 3, 7, 6, 1, 1, 4, 3, 7, 9, 2, 8, 8, 8, 8, 2, 8, 8, 8, 9, 3, 2, 7, 6, 8, 4, 2, 1, 3, 7, and 4, 7, 2, 3, 6. And there's your final sorted array.
Does this become less efficient the longer the numbers you're sorting out?
Yeah, this is the amount of work is directly related to how many digits you have and how many numbers you have to sort, and also how many possibilities you have for each digit. Right, so it's the length of the numbers and it's how many values you have for each place.
It's kind of like
How
n
many?
to the power of m, where m is the number of digits in each number.
Well, it's not too horrible. So if we do it this way, where we look for 0s, 1s, 2s, 3s, 4s, and so on, right? So it's your radix, right? If we're base 10, radix 10, then it's 10 possibilities, right? So we have to do that to get through one pass times number of digits times n, where n is the number of items you're sorting. So it's order n times the number of digits times whatever base you're working in. Well, if we're working base 10 and we're working with 10-digit numbers, this is order 100n. It's still technically order n. But this is where these orders of complexity can be deceptive. Right? This is saying that if n was big enough, this would look like order n. Well, let's look at another case. Suppose we do this in binary. Suppose we write these numbers out with just 1s and 0s.
only need one pass? 2 passes.
Depending on how you do it, 1 or 2. Right? We basically could go through and look for all the things that end with a 0, and then go through and look for all the things that end with a 1. So break it into 1s and 0s, odds and evens, right? And throw them into your output array in the same order. So the radix is 2, and suppose we're doing integers, and they're 32-bit integers. That's 2 times 64, sorry, 2 times 32, that's roughly 64n operations.
Should it be N64?
It should.
Sorry, I couldn't listen.
So that looks like order n, right? But think about this. Worst case, if we're working with numbers up to 4 billion, right? Let's say n is 4 billion. Okay, so we have every possible number that we want to sort. What's the log base 2 of n? What's the log n of 2 to the 32nd?
Oh, wait, just the longest 2.
Yeah. right? It's just the
It's 32.
exponent, right? That's where that 32 is kicking in. So for a reasonable set of data, say 4 billion integers, this might be order 64n, right, or order 32n, but 32 is actually log n, right? So this is different order of complexity, but in practical terms, the time's still going to be on the order of n log n. So it's not actually getting you a faster sort, but it's technically one with lower order of complexity.
So is that kind of the compromise when picking sorts is what's easiest to implement and what's easiest, or what's fastest, and kind of.
This is the classic n-way teeter-totter, right? Fundamental principle of computer architecture. You move this thing and everything else moves in response. So what's an ideal sort? Should be fast, right? Should be easy to code, although someone else will code it for us usually. Should not move things around in memory very often, right? Because computers work well because of locality of data. If you access one location in memory and you access other locations near there, your computer remains efficient. But if you access locations that are scattered all around the memory, your performance will bottom out because you're violating the idea of the cache. And that's going to hurt you. Sometimes you'd like a sort that preserves the order of things that are comparable, like when you're implementing a Radix sort. Sometimes you want to be able to work on data that may be partially sorted to begin with and not have that kill your performance. So there's all kinds of different approaches to choosing a good sort algorithm. And when I want to sort something, I just use the Unix sort command. I don't even know what algorithm it's using, but that's usually good enough for me. Another classic problem is if your data is stored on, say, magnetic tapes, right, and you have the option of moving from one number to the next very efficiently, but not the option of going backwards, right, and looking at other values. That's going to be really expensive. And something like a merge sort will work well for that kind of application because you're moving forward and sort of putting things together as you go. But in an older era where we had data stored on magnetic tapes instead of hard drives, right, that was a pretty critical criteria, is how often do you need to go back through your data, because every time you wanted to go back you had to rewind the tapes, and that takes minutes. All right, so Radix sort is a fun one. And you can do anything with Radix sort. You can do words pretty easily, but you can also do binary data, right, which means you could do a weird kind of integer sort.
So, it might sound like a noob question, but how would you look at the ones digit of a number in C?
Depends how you're storing them. So, I mean, if these are actually integers, you're going to have a lot of work to do, because you're going to be calculating modulo 10, right? So that'll get you the ones digit. And then, so you can do x percent 10 gives you the ones digit. And then you can do x divided by 10 as an integer. That basically shifts it over one spot. And then if you do that modulo 10, that'll give you the next digit.
And then x divided by 100.
Well, if you just keep dividing by 10, it's like dividing by 100 and 1,000. But that's pretty expensive in itself, right? So typically you would want to actually store each number as an array of digits. So this would be a 1 and a 3 and a 7. Or maybe just store them as an array of the actual integers that correspond to each digit. And now we can pull off, element 0, element 1, 2, 3, and 4. So this makes more sense for something like strings, right, where we have a notion of each individual element. But remember, Radix sort, you need to start with the least significant side first. And that's kind of weird with strings unless your strings are all right justified. Because if you just start with element 0, you're actually grabbing the most significant part.
Like if you end up storing them the other way, though.
Yeah, if you store them backwards, then you're good to
You have
go.
find them, like max val.
And these are like all these different subroutines that you have to do on
Yeah,
top
yeah.
of the sorting.
Yeah, and probably wouldn't make sense if your data was not already in that shape, right? You'd probably kill a lot of your efficiency going through and pre-processing. But if it was data you're going to do something with again and again, right, you might justify it or reverse it on the way into the system. If you do a radix sort with a different ordering, it totally doesn't work. So, right, if you sort these by most significant digits, and then you sort by least significant digits, you end up with that. If you sort by least significant, and then by most, then you get the right order.
So is that why, not for that, but what we were talking about before with putting them in backwards?
Mm-hmm.
I can't remember if it's like Word or something Microsoft, but they like put all the words in backwards. So that way when it dumps them out, it puts them out.
Really?
Like when we see it, it looks correct, but when it gets stored, it
Like they reverse the words, you mean?
I think so.
Really?
I couldn't remember. It was something we talked about in the 120. And I
Like
can't remember
pipeline
what
or
it was.
whatever.
Oh,
Yeah.
or maybe Illuminati or something.
Definitely Illuminati.
Backtracking Word documents. No, I haven't heard of that. I don't know if that might be related or not. It's interesting.
Because I could see that making sense for like, we want, the word "we are here," and so you wanted to start at the beginning of the array, so you just get whatever's ending, put it down backwards or something.
Right. Yeah, it could be.
So.
That's interesting.
So could you just, for sorting a string, convert everything to an ASCII code, add that all up, and then just sort the corresponding numbers that way?
I don't think so. I think it's got to be a weighted sum. So you're thinking about sorting integers that are stored as strings?
It's like you have a string, but each letter in the string would correspond to an ASCII character, right?
Okay,
Code.
right.
So if you added up each element after finding the value of the ASCII code, then you'd have a number that you could sort.
I don't think that gets you there because
1, 2, and 3 would equal 3, 2, 1, right? If you were to.
Well, you'd still have to sort the ASCII codes. So.
yeah, so ABC would add up to something bigger than CAA, right, which would make it think that CAA comes first. The reason this would come later is because this position carries more weight, right? So if you did something like this ASCII code plus 256 times this ASCII code plus 65,000 times this ASCII code, then you get numbers you could sort and they would alphabetize. And that's kind of thinking of your string as a big long integer that you get by laying out the bits side by side. But that's the whole weighted part of this weighted notation that we use for numbers. So it's a cool idea though. Is there anything like fundamentally inherent about the sort order of numbers? Like letters are random, right? It's because Big Bird sings that song. That's the only reason Cookie comes before a dog. But is there an inherent sort order to numbers?
You mean?
Well, I guess the obvious response is to say increasing order since they all.
Yeah. I mean, integers have this well-ordering property. 4 is bigger than 3 because you can add something to 3 and get to 4. But at some level, I think it's still a little randomish.
Are you saying like our instinct to sort by smallest to biggest or vice versa?
Maybe more fundamental than that. I don't know. It's just something that just popped through my brain and it's
Couldn't you
gone.
technically
I feel
add
like-
something to 4 to get to 3 though?
I feel like the invention of numbers is to order stuff.
Yeah, yeah,
So like that's
That's what I'm
its sole
wondering.
purpose.
yeah.
The only purpose it has is to order things.
Mhm.
So if I have 100 apples, wow, compared
Yeah.
to 2 apples.
It's just like time is an invention.
We don't want to go there.
Yeah, oh gosh. Oh, no.
Yeah,
That's a thing.
that is a thing. That's a whole nother thing.
It's a whole nother class.
Yeah.
Probably major, actually.
All right, so quick
Yeah, it's
sort.
called philosophy.
I almost got a job at a place that had the world's second leading expert on time travel working there.
Oh, wow.
Yeah.
Who was the first?
I don't know. It's like, what did this person do that you haven't
Watch the
done?
Fringe, and I'm pretty sure it's Peter Weller.
But it was this guy from Russia. All right, so quicksort. Quicksort is another n log n, usually, sorting algorithm. This one's a little weird to get our brains around sometimes, but let's try. It's a sort that's really hard to come up with good examples for, at least for me. So here's the idea of quicksort. We start off with an array of data, and we want to sort it. Let's go smallest to largest. That seems to be what we're doing in this unit. So we start off by picking what's called the pivot. And despite having a fancy name, the pivot's usually just the last number in the array. And here's the goal. What we want to do is rearrange this array, put the 20 somewhere in here so that everything to the left of the 20 is smaller than 20 and everything to the right is bigger than 20. So basic pass.
This is like the game War with cards.
Yeah.
Just like a quick look at the cards and then decide.
So move the 20 and arrange the array so everything to the left is less than 20 and everything to the right is bigger than 20. Okay, so this is the weird part of the algorithm. So we use a pair of indices. Our first index begins at the leftmost position, and our second index begins at the rightmost position. Okay, so we begin on the left, and we look at the number we're looking at, and we say, is that smaller than 20? And it is. So we move over one spot to the 23, and we say, is that smaller than 20? And it's not. So this is in the wrong position relative to 20. In some vague sense. Okay, so we leave that there and we come over to our second index. And here we're looking for things bigger than 20. So is 47 bigger than 20? Yes. So we move over one. Is 3 bigger than 20? No. All right. So 3 is smaller than 20. 23 is bigger than 20. These are in the wrong order. So yes, we want to swap these. So we're going to let them change places, and now our array is going to look like 14, 3, 7, 30, 16, 45, 11, 18, 23, 2, 41, and this became our 23, our 47, and 20 is still our pivot. And so this was our first index, and this was our second index. And we keep going. We're going to keep moving these indices until we get to things that are in the wrong position. We're going to swap, and we're going to keep moving, and eventually our two arrows will collide with each other, and then we're done. Okay, so let's keep moving. So 7 is smaller than 20. That's good. So 30 is not smaller than 20. We stop right there. We come over here. 41 is bigger than 20. That's fine. 2 is not bigger than 20. That's a problem. So now we're going to go ahead and we're going to swap these. And now our data is going to look like this. 14, 3, 7, 2, 16, 45, 11, 18, 23, 30, 41, 23, 47, and 20. And we were sitting right here, and we keep going. So 16, that's smaller than 20. 45, that's not smaller than 20, that's where that stops. 23, that's bigger than 20. 18, that's not bigger than 20, that's where that stops. And we swap these. I put my writing up here too high. So 14, 3, 7, 2, 16. This becomes an 18. That becomes the 45. And we're sitting right here, and we're sitting right here. All right, come over here. 11 is smaller than 20. Move over again, and we've collided with our arrow. So now we're done moving our indices. And so at this point, we take this element and we swap it with the pivot. And that gives us our final array. So the 45 gets replaced with the 20, 23, 30, 41. I got an extra 23 somewhere. Oh, I had two 23s. That's cute. And then a 45 over here. And this was our old pivot. Okay, what the heck have we done? Because this is certainly not a sorted array, right? But everything to the left of 20 is smaller than 20. Everything to the right is bigger than 20. What does that tell us about this number 20? It's in the right spot. This is where it's going to end up when the entire array is sorted. Because when we sort it, everything to the left has got to be smaller. Now these are going to get rearranged and these will get rearranged, but these are all going to stay over here. These will stay on the right side. So 20 is going to stay right there. So now all we have to do is sort this and sort this, and we're done. So how are we going to sort this subarray?
Pick the end number, repeat.
Yeah, we're going to use quicksort. We're just going to call quicksort on it, and we're going to call quicksort on the thing to the right of the 20, and then we're going to be done. So what's the complexity of this? This basic operation, we're moving and moving and moving and moving, and then we're going to swap, and then we're going to keep moving, and we're going to swap, and we're going to move and swap, and then we're going to finally take that and swap with the pivot. What's the complexity of that? Roughly how many operations? It's order n, right? Because we have n pieces of data to go through. Each number we're going to have to compare to our pivot, and swapping, that's 1 or 2 or 3 operations, right? And we're going to have to do this until our arrows meet. So we're going to go through and compare a total of n values to our pivot. So that's order n. And when we split in half, right, we're going to have to quicksort each of those, and those are going to be order n. But eventually we're going to split our array down to where we have a single element, and just like a merge sort, we don't have to do any sorting for that. That's already sorted. So the number of times we're going to have to do this is basically log n. And each operation is order n. So this is generally n log n. Same as a merge sort. But one of the downsides to quicksort is if your data is sorted to begin with, So we're going to start here. This is smaller than our pivot. This is smaller. These are all smaller than our pivot until we come down here. And so that tells us that we need to switch this element with itself. In other words, this is already in the correct position. And then we're going to call quicksort on the right side, and there's nothing to the right. And then we're going to call quicksort on this subarray to the left. And if we started with n elements in our array, now we're calling quicksort on n minus 1 elements. And when we do that, this will be in the correct place. We'll call quicksort on n minus 2. So we're going to call quicksort order n times instead of log n. And each pass of quicksort is order n. So this is going to be order n squared if your data is sorted to begin with, or close to sorted. So unlike Mergesort, the performance of this depends on how your data looks to begin. And so sometimes you randomize your data before you start sorting in case it was almost sorted initially, just to jumble it up and avoid this kind of pathology. All right, so that's quicksort. So let's do 5-minute break at the most. Let's come back at 1 o'clock and we'll go through heaps. And I want to get through all of heaps today, and then we can rehash this stuff on Wednesday. Rehash, sorry.
If you already had sorted data like that, you're pivoting at the very end, would that end up being order of n factorial?
No, I think it's still n squared,
Okay.
because your central pass is still order n,
XR 290.
but
So curious, like if you're doing 10 and then you're doing 9, 8, yeah.
yeah, you're adding them though.
Oh, yeah.